Hello, and welcome. My name is Josef Jakub Kojda, and I'm from Slovakia. I'm a student at Cambridge International School in Bratislava. Today, I would like to talk more about infinities. I was inspired by my girlfriend to make this video. She told me about the film Fault is in Our Stars. One of the characters there mentioned that there are two kinds of infinities, and she asked me whether that's true, and I explained it to her. I wonder if there are more of you. If yes, this is absolutely video made for you. So let's start, guys. So before we move on to proving two kinds of infinity, I would firstly like to talk more about what actually word infinity means. And what should you imagine when somebody uses this word in math? Infinity is an unbounded quantity which represents something indefinitely and unmeasurably big. In math, we usually speak about infinite number or about infinitely many items included in a set. Before we move on to the main point of the video, I would like to mention one more thing. This is something really important. When we are comparing two groups of objects, or in math two sets, we don't have to necessarily add them up and then compare the sums. We can do following thing. Imagine that we have two groups of sheep placed in a sheep house and we want to know which group is bigger. I think it is really challenging to count them mainly when they are moving around constantly. So we will take another two sheepfolds. These two original sheepfolds I will mark as A1 and A2. And these two are going to be B1 and B2. Each time shepherd takes one sheep from A1 and move it to B1. And same for A2 and B2. He does so until one of sheepfolds is empty. When it is empty and there are still sheep in another one, he knows that the group that was placed in empty sheepfold is smaller. If we would like to represent this method in more numerical way, think about it as comparing numbers based on how many times you can subtract -1 until you get 0. Okay, and now comes the main point of my video. Cantor's proof of two different infinities. We are going to use pairing up method that we used before to pair sheeps. Now we are going to compare two sets with infinitely many items included in them. One of them is going to be a set that includes all fractions, and the second one is set that includes all natural numbers. I think you all agree that both sets include infinitely many items, because we simply don't know how many natural numbers do we have in total, and the same thing works for fractions. Now, I'm going to list all fractions in a way that I can be sure no fraction is missing. I'm going to list them in kind of a triangular form. I think all of you can clearly see the pattern of writing them down. Column number describes the number in numerator and row number describes the number in denominator. Therefore, we can be sure that this is a complete list of all fractions. I know you may argue that 1/2 is the same as 2/4. Yes, it has the same value and it represents the same number. However, it's still a different fraction. Moving on, now I'm going to assign a pair from natural numbers to each of fractions. I'm going to write them down diagonally so you can clearly see that every fraction from the set of fractions has a pair from set of natural numbers. Therefore, I know that set which contains all natural numbers equals to the set that contains all fractions, which means that there is same amount of natural numbers and fractions. So the infinity that describes the number of fractions is the same as infinity that describes the number of natural numbers. Let's think about a set that includes all real numbers between 0 and 1. I would like to emphasize that all of them. That means that no number is missing. I will try the same thing as I did for natural numbers and fractions, just for natural numbers and real numbers. I am going to list natural numbers one beneath the other and then write the pair from the set of real numbers next to each of them. So next to 1 I will write 0 point and then denote decimal digits as A1, A2, A3 and so on. Next to 2 I will write number 0 point and then again denote decimal digits B1, B2, B3 and so on. The same for 3, 4 and I can carry on with this. Assuming that I listed all of them, now I will come up with a new real number and call it x bar. I will denote decimal digits of x bar as x bar 1, x bar 2, x bar 3 and so on. Now, check this out. I will state that A1 is not equal to x bar 1. That means that x bar has different first decimal digit as a number paired with 1. In connection to this, I will state that B2 is not equal to x bar 2. This guarantees that second digit of x bar is not equal to second digit of the number paired with 2. The same thing I can do with x bar 3 and C3 and x bar 4 and D4 and keep doing it basically forever. The most important thing about this is that the property that I made up for every decimal digit guarantees that x bar is not included in the set of all real numbers. As from first number, it differs for sure by third decimal digit, from second by second, from third by third one, and so on. Therefore, it is not included in the set of all real numbers between 0 and 1. In consequence, the set doesn't include all real numbers and there is a contradiction. Therefore, the pairing between real numbers and natural numbers doesn't work. Because my x bar doesn't have a pair, it is not included in the set. This means that there is more of real numbers between 0 and 1 than natural numbers. Although there is an infinite number of real numbers and infinite number of natural numbers, there are more real numbers than natural ones. This means that there are two differently sized infinities. Infinity that represents number of natural numbers is called Aleph 0, and infinity that represents real numbers is called Aleph 1. So that's it, guys. Hopefully you enjoyed my video and learned something new as well. Before the end of this video, I would like to ask you a question connected to infinities. Imagine that you have a line of length 1 and second line of length 2. Both of them have infinitely many points included on a line. However, as you have just seen, the fact that they have infinitely many points doesn't necessarily mean that they have the same amount of points. Please, think about it and either prove it or disprove it. Any good ideas are welcomed. Leave your ideas beneath the video in commentary section and I will publish my solution to this question on 11th of October.